clocks. Are you guys ready with the clock over there? Full screen.
Okay.
Zoom to fit. All right. Guys, seriously. Neville, start. Talk loudly.
Talk loudly. All right.
Louder.
Well, I'm starting.
Louder.
I can't talk much
louder.
Come on. I'm Neville. Yeah, that works. That works fine. I'm Neville Brownlee to talk about some work we've been doing on high-speed data transfers. This is none too gentle pushing of TCP, really. Se-Young Yu is the student who's actually done most of the work here. And the starting point is there are lots of big projects, big science projects with heaps of data to move around the internet. They can afford their own dedicated fiber all over the place to do it. We can't. So we're looking for ways to get as high a transfer rate over as long a period as we can for whatever data we're moving. We've been very fortunate in doing this to have kind friends with fast networks. So that's just an outline of those networks. But the interesting part was one from Queenstown in New Zealand all the way across to Stockholm in Sweden. And the section from Queenstown as far as Chicago was 100 gigabit per second network and 10 gigabits from there across through internet to and Giant into Stockholm. First thing, you've got to have really fast disks. That is very obvious. Although it's mildly interesting when you look at that left-hand graph that UDT didn't seem to suffer as much from slow disk performance. On the right-hand plot, we can, of course, run multiple flows at the same time. And in principle, if one flow gets X megabits per second, 5 flows will get 5 X bits per second. But we also know it doesn't always happen like that. So here's a couple of pictures. These are pulled out by a moderately simple Python program from trace files. The left-hand side shows a single transfer, and we're looking at the number of bytes in flight on the wire, on the y-axis, over time on the left. And the one thing that really leaps out at that, good heavens, it's a 50 megabyte TCP buffer running through there. On the right-hand side, we've got 5 flows doing the same sort of thing. And now you can see, well, we've got 5 times as much TCP buffering, which means we can expand the effective TCP window 5 times as fast. And that's most of the reason why the multiple buffers, the multiple streams work better. And the little triangles are showing when packets get lost, and you can see that the flows are very much synchronized. The other thing we're interested in is some notion of fairness. Basically, we think we should grab all of the available capacity on the network as long as we don't get too much in the way of other people. And the only way we've got of determining that is to look at the round trip time and see what effect we're having on the round trip time. So the y-axis on both the plots is the round trip time. Okay. And I'll make one last remark, which is it's amazing how much you can get out of a simple Python program and some trace files. Thank you very much.
Hi, I'm Qingwen Hu. I'm from Auckland Uni. I did this work with my supervisor neighbor last year. So what we try to looking for is like we try to understand how network administrator to allocating IPv6 address for server and for client. So we have like running our Python libtrace for 1 month and collect the data from our university campus. We're looking at the incoming and outgoing IPv6 address, and we only look at the bottom 64 bits, which is called interface identifier field. The reason we're looking at this one because we found some network administrator using like a customized RID allocation schemas, which can cause the network attackers to use that to reduce the searching space. Also, we found some existing allocation mechanisms has few security and privacy issues. So by summary is that we try to answer 3 questions in our studies. We try to understand how easy to scan the values in IID field, which is related to security part. Also, we try to understand how easy we can find the IP version 6 host by looking at the IID field, which is like we look at the visibilities. Also, we try to understand how easy we can track the user activities by monitoring the IID field. Here are some results from here are some samples from our result. So we have categorized like all the allocation schemas into 2 catalogs. One is recommend IID allocation mechanisms, which is from the standard IFC, and also some customized IID allocation mechanisms. So the first one is EUI64. What they have been used is using the host MAC address plus 2 significant patterns, FF and FE. And the second one is random and privacy. This field will randomly change when the host move from one network to another network. Also, it will change based on the timeout. And then we notice like some customized IIT allocation schemas, which is like a network administrator using field bytes for non-zero values and then leave the remaining space as 0 values. Also, they like to put some IP version 4 address into IP version 6 address. So by comparing those allocation schemas, we found UI64 has a high visibility, but with a low privacy and no security. Random and privacy schema with a low visibility, but have a good privacy and security. So here's our result. So the server side, people like using small integers because it's easy to find. But from the client side, they like to use some randomize because it's quite secure.
Hi. I want to briefly talk about countries, IXPs, and RIPE Atlas. It's a fun little project I've been developing using RIPE Atlas probes and subselecting probes from the huge volume of probes we have, about 1,000 in France, for instance, to actually do a mesh of trace routes between these and collect these and have a framework for analyzing them. So simplest config is there. It's a simple JSON file. So this whole thing has a couple of script sets, steps, and one of the steps is an analysis step, and you get out 3D pictures like the path from probes, RIPE Atlas probes in Japan to RIPE Atlas probes in Japan, and here you can actually see some of these paths go to Hong Kong. Paths are not traffic, and there's a lot of limitations to this type of data. For instance, it uses OpenIPMap, which is a crowdsourced geolocation specifically for routers. It has errors. We have biases on where we can place RIPE Atlas probes, where there are no probes. But this gives you an idea on what variation of path can we get out of RIPE Atlas within a given country. You can add IXPs in here. You have to add some config on the peering lens, and you can actually see, for instance, can we see a path going out of country, not going through an IXP, which is red here, or path going through an IXP that you infer are staying in a country, which are green here, and this is a result for Japan. That's the URL for if you want to see this. This may crash your browser because it's all rather prototypey. Many more features. You can select do 2 countries, for instance, Argentina and Chile, and see if they actually directly, or if you can see path going through Miami. Yes, you can. It's modular, so it should be easy to add, and it's all on GitHub. And I would love other people to actually help do stuff and help understand what these actually mean, these diverse paths that we have. That's it. Thank you.
Yeah, good afternoon. I think I should stand more or less here. So I'm going to talk here about how dynamic the IP address space is on the internet. And on the questions we know, that's like ISPs, they get the bundle of IP addresses, but nobody really knows how they use these IP addresses, how fast they churn through the pool of addresses that they have. So this work is exactly a kind of active probing internet wired scan to determine that. And we could only do that because we had access to private data. So I'm going to show you that. But we also validated later with the RAIM probe. So our problem basically was like the dot counts were based on counts of IP addresses are not really valid because different ISPs have different policies. Nobody standardized actually how long IP churn should last. IP address lease, the HCP lease. So it can be 1 day for one provider. Usually Deutsche Telekom apparently is used 1 day for home users, but it can be a month. So if you use IP addresses as unique identifiers for counting of unique hosts, it's pretty hard because you don't know how many unique hosts are behind that. So what I try to do is to measure DHCP churn so we can compensate for the effects of churn when you count unique identifiers or hosts. So today I know SMMP has been severely bashed here, but as a protocol that kind of helps us here. And what we do, to summarize, we probe the entire autonomous systems every 10 minutes using SMMP. That's it. And then you compute the uptime. There's more details on how to do that in the paper. It's kind of simple. And the good thing that we had access to the ground truth data of one ISP. It's in the Middle East. We conducted our measurements from the Netherlands. And we're 1 million IP addresses. So I think this is like maybe the most comprehensive study, even though it's kind of small, using ISMP reachability and validation for uptime. And first we have to understand what actually do they have. So internet service providers, they have a bundle of addresses, but they divide in pools. Those are the red dots in here. And this is the radio servers and the pool, the share of addresses that each radio servers get. And this is the ground truth data. This is like how many IP addresses per day, per use they have. And this is a very dynamic ISP. Each IP had roughly 15 users per day. And this is the results we got. So 72% precision estimating DHCP churn only using ISMP remotely. This was pretty good, simple method that works. And we also validated with RAIM probes. Later on, it works even better. And that allows us to get the pool of addresses via ISPs. And these are different ones. It's under submission now to severe communications. And we can see what is the pool that's static, dynamic, highly dynamic, and how dynamic they are. And I think that's it.
So I've spent a bit of time working on measuring and understanding the deployment of TCP over a few years, and I would be very much interested in engaging with the IETF and pursuing relevant tests in the next couple of years. Just to give some sort of history in terms of what I've done in the past and maybe things that I can help with in the IETF. And in 2010, we did some work looking at the behavior of path empty discovery if end hosts are responding to packet debigs. And we found, in fact, a whole bunch of sort of bugs that we contributed back to operating systems, particularly FreeBSD. And then just recently we looked at, in both of these papers with students, at the resilience of TCP to blind attack. So looking at an RST that came out of TCPM, how much of that has been deployed, and we found that there has been some reasonable deployment, but there are still plenty of systems with plenty of perhaps work to be done. Over the years, we've spent a lot of time implementing tests into Scamper for doing the typical T-bit tests. And yeah, as I say, you can take a look at the papers that we've got down there at that webpage, but would really appreciate engagement with the IETF in some way.
All right, so I'm Colin Perkins from the University of Glasgow. So we did some work in IETF a few years ago, leading to RFC 6679, which was describing how to use ECN with RTP running over UDP transport. This is nice, at least in theory, because it allows you to improve the QoE, which is, of course, a wonderful word we all love, for interactive multimedia by avoiding packet loss and reducing the delays, and by letting the applications control how they respond to congestion, rather than forcing them to recover from unplanned packet loss. That's something that's potentially useful in the IETF now, because some of the proposals in the RMCAT working group use ECN for the basis of their congestion control, so they can well build on this. It's also something that's potentially useful for protocols like Google's Quick, which are starting to layer over UDP for things like SPUD, which again are layering over UDP to provide generic transport. Hopefully they can all use ECN. We also did an initial measurement study, which we presented in IMC last week. This leveraged the public NTP servers to test the usability of ECN with UDP. The plot is showing a trace route from the middle around to 2,500 NTP servers using ECN marked UDP packets. The green is showing where it works. The red is showing where the ECN marks get stripped off. Details in the paper there, but we see middle box interference on only about 1% of the routes, and that doesn't affect reachability in the overwhelming majority of cases, much more than that, 99.9% or whatever it was. I forget the exact number. So we're interested in working with the measurement community to better understand ECN usability. This is clearly a very early study. It tests a very limited set of protocols. And we're interested in working with the IETF to raise awareness of the utility of ECN with UDP-based transports. Thank you.
Hello, everyone. This is Zhe Lai from Tsinghua University, and today I would like to introduce some of our work about the personal cloud storage service. And this work was accepted in the ACM MobiCon in this year. As we all know, the personal cloud storage service, just like a Dropbox or Google Drive and Microsoft OneDrive, are very popular in recent years. And this service also contributes a very large amount of traffic to the internet. And so in this work, we identify and analyze the sync inefficiencies problem in current cloud storage service. So we measure and analyze the some typical cloud storage service, just like Dropbox, Google Drive, and we measure their network trace and study their sync protocol. So we found three issues, and the first one is the more efficiency the duplication used by this service does not work well in the high delay conditions. The second one is we found that the incremental sync of this service always may fails in some conditions, especially for some file operations. Another finding is that we found that some service suffers the low bandwidth utilizations because of the caused by the slow start and the APT level ACK. So further, we design a new framework to improve the sync efficiency for this service. We combine the storage techniques and networking techniques, and for more details, you can read our papers. So in the future, I think we still have much work to do in this field, maybe from the usability and improve the performance, and also because many current mobile apps are built on those cloud storage service, we also can consider energy efficiency problems. So maybe a possible solution maybe is we can design a standard sync protocol for this storage service, and we also prepare a board on the IETF next week, Tuesday afternoon. So if you are interested in this topic, we are welcome to our board, and we sincerely hope to get your suggestions and comments. And this is our mail list. Thank you.
Hi, good afternoon. I'm Ines Robles. I belong to the Metrics project, and my research topics is focused on measurements for IoT constrained environments. Basically, my goal is identify the traffic patterns depending on use case for IoT. For that, we are going to take measurements.
No, keep going, keep going.
And for that, we are going to take measurements in the high layer using the Lightweight M2N protocol. That is device management protocol developed specifically for constrained environments. And we think that we can extend the LMAP functionality framework for it's a protocol developed for in LMAP working group in the ATF. So we think that we can, okay, in the LWM protocol, the client and the server are part of the standard, but the proxy is not. But we use that for group management devices. So we think that we can apply the functionality of the controller and collector in the proxy and the management measurement agents in the client and in the server. And as well, these two kind of protocols have data model based on object. And I would like to use IPSO object as a data model. Okay, that's all. Thank you.
Hi everyone. So my name is Mohammad Waif Anwar, and I'm a PhD student at Steubenberg University. So how do we innovate in the internet? So we can innovate by building new protocols, changing the existing ones, and playing with those all what-if scenarios. But doing this meaning testing new ideas straight on the internet, which might require internet-wide changes, and this might cause disruption in the internet. So what's the solution? So we use internet models for that. We can use internet models of routing policies, AS topologies, and traffic matrices to accomplish these goals. So is the problem solved? Not really. We don't really know how well these models actually perform. So now standard model of routing policies was put forward by Gao and Rexford in early 2000. According to this model, ASs connect to each other based on their business relationships. That means AS can have a customer-provider relationship in which customers pay the transit cost, or they can have a peer-to-peer relation in which both ASs generally exchange traffic at no cost. According to this model, an AS will always prefer a customer path over a peer path over a provider path, and they will always pick up the path with shortest path length. As far as export policies is concerned, a customer path is exported to all neighbors, while a path from provider or peer may be exported to customers only. But how will this model actually hold? So we selected a couple of thousand RAIM Atlas probes from different countries and different ASs. From these probes, we issued trace routes towards selected content providers. So we selected content providers like Facebook, Google, Amazon because they carry majority of internet traffic. Finally, we compared the AS paths from these trace routes with GAR expert compliant paths from CADA's AS topology. And then we measured how much of these paths actually followed GAR expert model. So 64.7% of total decisions followed GAR expert model, but still there were more than 1/3 of the decisions that didn't follow the popular model. So what was the cause of limitation? So one of the cause of limitation that we found was sibling ASs. Sibling ASs are those ASs which belong to the same organization. So many organizations have multiple ASs due to maybe commercial mergers or due to different geographical region. Another cause we found was prefix-specific policies. So inter-domain routing is often abstracted to the level of destination AS. However, in practice, routing is done based on IP prefixes. So ASs can have different export policies for different prefixes for same AS. So this is also one of the cause of limitation. Another cause of limitation we found was undersea cables. So combining all these limitations and some others that we studied, we found more than 20% of decision can be followed by GAR expert model. And yeah, future model can improve if we take into account these limitations. For details, refer to the script.
Hello, my name is Megumi Ninomiya. I'm working at IIJ Research Laboratory in Tokyo. I would like to talk about playback delay inference for HTTP-based live streaming service. First of all, I would like to introduce about live streaming for Summer Koshien. Summer Koshien is a baseball game championship. It's an annual event and the largest sporting event in Japan. all of games are broadcasted on TV, and live streaming service was provided all of games too. For 2 weeks, there were about 50 games. I'm sorry. And people can watch that live streaming by the PC and smartphone browsers and dedicated Android and iOS applications. Usually, games start from 8 a.m. and end around 6 to 7 p.m. So most of games are played during the daytime. Then people watch the live streaming by PC and mobile device during commuting and working. Asahi Broadcasting Corporation and IIJ provide HTTP live streaming service for Summer Koshien. The last year, 38 NGX server were used, and 1.9, the total request was 1.9 billions, and peak traffic was 108 gigabps. It was recorded during the final games. Actually, for HTTP-based live streaming, there is a playback delay, even though we say live. And the length of playback delays differs depending on viewers. It means viewers watch the different scenes at the same time. How much playback delay is there? We are not sure. And if we want to measure it, it will be expensive. So we propose the estimation method for each player's playback delay from only web caching server logs. And by using the method, we estimated the length of playback delays and distribution of it, and most of the major cause of playback delays. Here is our proposal playback delay model and estimation method for the playback delays from server logs. And we found the segmentation and startup buffering are big factors. And the vast majority of the playback delays are within the range of mean plus minus 2 segment lengths. Playback delays are measured from server logs, and the delay calculated by the proposal models are almost the same. Thank you.
Yeah, so at Apple, in the latest iOS and OS 10 release, we deployed TCP fast open, and we did a lot of experiments with ECN, and we learned some very interesting lessons with this with respect to mailboxes. So TCP fast open, as probably most of you know, is an extension to TCP that allows to send data together with the SYN segment, and it uses some TCP options as well for signaling. ECN as well uses a specific bit in the TCP header to negotiate, and later on uses the ECT bits. Now we know that there are mailboxes out there that are dropping segments which have unknown TCP options, or might drop segments with SYN segments that have data, and so these kind of things have actually been very well studied, and so we can handle this very easily by just when we are retransmitting the SYN, we don't use the TCP option anymore. Same for ECN. There have been measurement studies that measure how the SYN gets through and how many servers reply with an ECN bit. However, in terms of mailboxes, the fun actually just starts there. So we found actually in our deployment that there are mailboxes out there that start blocking a flow when using TFO after the three-way handshake. So in the example that I'm showing here, we found one mailbox where TFO works fine, the server acknowledges it, it even starts sending data, the client sends the third ACK, and only after this, the flow gets broken, and nothing works anymore. And it's not only this flow, actually all traffic that goes from this client to this server is being black-holed for the next 30 seconds, and then everything's fine again. And so, yeah, these kind of things were actually pretty, we are pretty surprised when we found this, because the flow was already established, so everything should have been fine. For ECN, we found similar things. For example, there was an ISP that marks every packet with a CE bit, which is not very optimal when you're using ECN. We had ISPs. Actually, this is pretty common. We have ISPs that are reordering packets randomly when ECT bits are being set. And so the impact of TCP extensions actually goes far beyond the TCP handshake. So those kind of extensions might confuse mailboxes, might reveal bugs in those mailboxes. And customers that are inside those ISPs, they will just have a broken connectivity. And so we'll have to take those kind of things into account and develop heuristics to basically fall back to regular TCP. And so, yeah, on Monday at HOPS, there will be more details about the findings that we had around ECN. And on Wednesday at the TCPM meeting, we'll be talking about TFO a bit more when time permits. Thank you.
This was you, right? Sorry.
Hi, I'm Yves Nobel from the University of Liège in Belgium. And today I will speak about MPLS. So MPLS means multi-protocol level switching. As you know, between an entry and an exit points of a tunnel, you may have multiple paths. And these paths are called LSPs. Our motivations is to study the actual usage of these paths. So we developed LPR, which means label pattern recognition algorithm. This algorithm is able to reveal the actual usage of transit MPLS tunnels, so the paths between entry and exit points, depending on their usage. Everything is based on the label distribution and the IP addresses. LPA works in two steps. First, filtering steps. It isolates MPLS transit tunnels from the dataset. It's an offline method, so you first collect different traceroute data and then apply LPA. After the formatting steps, we have the classification steps. Here we have 4 different classes. The first class is the mono LSP, meaning we always have the same path between the entry and the exit points. Then we have multifec, meaning we have some traffic engineering. Then we have the monofec class for load balancing, equal cost multipaths, and finally unclassified if we did not succeed in classifying the different paths. So we applied LPR on a huge data set of 5 years of traceroute data between January 2010 and December 2014. What we observed is that MPLS is more and more deployed. In the last years, about 50% of the paths, traceroute paths, contained at least one MPLS tunnel. And concerning the classes, MPLS is mostly used in its basic usage, meaning mono LSP class, so always one path. But after this, we have some equal cost multipaths, so load balancing is quite present. And finally, we have multifec, so the traffic engineering, but it's more rare, and all the results are AS dependent. Thank you.
Hello, Alberto from CADA, UC San Diego. This work is about inferring which portions of the address space are actually used. So we group IP addresses in /24 blocks, and then we say a /24 block is used if at least one of its IP addresses is assigned to a machine that transfers packets on the public internet. So why do we care about it? First of all, there is no public dataset that answers this question. And besides aspects related to policy, and so understanding address space allocation and address space allocation, there are, research on policy and on economics is interested in understanding internet usage over time. And the results of these projects are also applicable to security and operations. So, for example, results from these projects can inform host reputation systems. In few words, how does our methodology work? Basically, we combine traditional active probing approaches with novel passive measurement approaches in which we look at traffic and traffic logs from different vantage points distributed worldwide. Sometimes this traffic is sampled, sometimes is unidirectional, so there are several challenges involved in performing our inferences. One of the biggest challenges typically is identifying spoof traffic, so packets with source IP addresses that are fake, and they heavily impact our inferences, of course. This graph here shows our classification of the IPv4 address space in 5 categories. And here in this graph, I would like you to notice just 2 things. The box in the middle, the unrouted assigned at the bottom, it shows 3.4 million /24 blocks. 20% of the IPv4 address space that is actually assigned in 2013 was assigned to organizations, but was not even announced on BGP. So definitely this wasn't used on the public internet, right? And then the second thing is the 2 blocks at the bottom on the left, the used and routed unused. They show that according to our inferences, a large fraction of the address space that autonomous systems originate, announce on the internet, on BGP, sorry, is actually not utilized. So the paper, and there is also a website on the link, is packed with that analysis from different points of view, geographic, BIS, administrative, domains, RIRs, and so on. So I invite you to go on the website and check the visualization. And yeah, this is an ongoing project.
Hello, my name is Kamei Satoshi from NTT Communications. NTT Communications is a tier 1 global carrier and one of the most largest ISP in Japan. My research motivation is focused on structural analysis of the internet using end user probe and with active measurement. Because we have some internal traffic measurement data and BGP routing information, but we cannot predict content providers' behavior. It is very difficult to predict, especially in hypergiants. So I will show you the CDN analysis for iOS 8 update and Windows 10 update. This is our measurement system. There are about 150 active probes. They are set up connected to residential FTTH access environment. This figure shows daily trend of the throughput from another different ISPs and different regions. This slide shows DNS response analysis from 9 ISPs measurement. It uses DNS response data. X-axis shows timeline and Y-axis shows DNS response rate by AS name. Start point is the day of the iOS 8 update was started. This app used their own AS before update, but after update, most of their traffic is offloaded to Akamai and RAIM. This behavior is different in each ISPs. This slide shows Windows 10 update. Microsoft use a little for their own AS, and most of the traffic is Akamai and RAIM AS. So most of internet traffic is not operated by BGP routing, but DNS or some other application layer control. So end user active measurement is a very effective method to know what happens.
Hi, my name's Kevin Fall. I want to talk to you about compact routing a little bit, and I have the, I guess, honor of submitting probably the oldest paper, which was from 2004. And the reason I wanted to do that is because I think this topic has not received enough love in the last, I don't know, decade and a half. And the nod is to some work that actually was with Dmitry Kryakov, who was at CADA at the time and is now at Northeastern, and has actually gone a number of other ways past this work. So I know some of this group is familiar with this stuff, but I'm guessing a number of you are not. So compact routing is this area of work that came out of graph theory that says we can actually do routing in pretty efficient ways if we follow certain algorithms. A routing scheme is an algorithm to establish a set of paths in a graph and the forwarding data that goes with it. And the big trade-off is how much information do you put in nodes that are doing the switching versus how efficient is the path. Normally in this sort of the classic textbook, we learn about what's called stretch one routing, which finds shortest paths. But it turns out if you're allowed to relax that and you induce a metric that is the ratio between how much distance you take divided by the optimal path, you can get big gains in the amount or in reduction in the space of the table. So all of that says a scheme is compact if it has tables that grow sublinearly in the size of the number of nodes, has bounded stretch, which is this ratio, right, of under the routing divided by the optimal path, and log n header size. A universal compact routing scheme is one that covers any graph. So this gives us the square root result, which is square root of n with stretch below 3. This is a result from 2001. And there's some other follow-up work. The most interesting thing is you can label the nodes any way you want. They don't have to be labeled in the same way as according to the topology is a sort of a meme here, and you still get the same results. Where this connects with measurement is that the graphs that so this work that I did with Thema that was in the paper that I submitted was that if you take this algorithm that was done in the graph theory community and you dropped it down on the topology that we knew from the time and that it looks like it's continued, it works very, very well. So which is to say that the stretch is a really small number, barely above 1. And that's pretty remarkable. There was follow-up work. This is a case where it went from the theory community to the measurement community and back again, where there was subsequent proofs that showed that this type of routing on scale-free graphs, which are this sort of properties we have, actually works really well by proof. So, and that's this additive stretch result. There's also some other folks here, and Colin is here, and Stephen, who will talk later, also followed that up in his thesis. So what? So it's theoretically attractive and that you can get these kind of results. Hierarchical routing doesn't work at all in the type of graphs we actually have, which is unfortunately what we're faced with in this community. But can we make a compact routing-based protocol that will work in an internet type of use? And that is the problem there is that the graphs are dynamic and they change. And there's one other line of work to consider, which is that you can take a topology and you can embed it in a metric space and route on that with basically geographic routing.
Hey everyone, I'm Eric Osterweild. I have a very short presentation which works well with the fact that we're coming up on the end of the day. So this is work that was done with some people that I failed to put up on the slide, but are referenced obviously in the citation paper. And we took a look at how you could actually measure and quantify one version of a network system's attack surface. And to illustrate that, we actually compared a couple different things. We compared the web PKI and a new suite of protocols being standardized called DANE. So my one slide of content is this one. In the paper, we outlined a couple of things that we found. One of them was that we could come up with a candidate way to link together different types of network resources or different types of systems resources in a causal relationship. So you could have things like DNS resolution systems that eventually tie into certificates and certification authorities, back down to TLS keys, et cetera. And when we were looking at this, we had this we ran into a number of people that said to us, when I deploy servers richly, why is it that that increases my attack surface? If, for example, they're all slaves and they can't lie. And so it helped us refine a notion in the paper. We outlined a sort of proposal that availability and verifiability are actually not necessarily the same thing. So through using, for example, DNSSEC, we propose that you can actually measurably reduce your attack surface over just using regular DNS, because a lot of the nodes that you use to service traffic can't actually lie according to the protocol. In other words, they're detectable. So we had a sort of a cute little graph. I don't know if I have a pointer on here or not. Yeah. So we had a cute little graph of taking the same sort of Alexa top 1000 and measuring those and showing, more quantitatively in the paper that there's a really big attack surface reduced greatly by applying DNSSEC, and then we measured it down here. And that's it.
Hi, so I'm Stephen Strauss, and I'm not going to talk about compact routing. I am, however, right now paying a lot of attention to IPv6 within Yahoo and what we see from outside of Yahoo. So we spend a lot of time paying attention to eyeball networks. I have two primary data sets that I'm paying attention to. One is HTTP logs that we gather from our content distribution networks that forms the basis for the data that we provide to the Internet Society every week. And the other data set that I pay attention to is mobile data reporting to Splunk. So I get to actually see server-side reporting and also client-side reporting. So we're all familiar with the notion that IPv6 is now 10% of the internet, depending on who you are and where you look and what day of the week it is. But of course, that's not evenly distributed by ISP or by geography. So our HTTP logs sort of point us at, once we do our IP to ASN mapping and bundle those up into ISPs and bundle those up into countries, we wind up pointing at quite a lot of IPv6 traffic coming in from Europe, quite a lot coming in from the US, and these are big numbers. We probably have around about 15 or 16 countries right now coming in at over 10% according to what we are measuring. The other interesting side is when we look at the Android reporting. When we look at Android specifically over LTE, we're at about 1/4 V6 globally. If I pin down on one major US cell network, what we see is close to around about 90% V6 end-to-end native. If I look at that on an edge where Yahoo is not dual stacked, it's still 90% V6 on that particular network because they're doing a ton of NAT64. This has some fun implications because we get insight into NAT64 from inside the ISP and additional implications because it breaks DNSSEC and that kind of thing. But a plea, if I can make one. We had a ton of papers at IMC this week that spoke about IPv4 as the whole internet. And I would argue that that's not the case and that we should really sort of move on from that and try and apply a lot of our measurement work to IPv6 and IPv4 wherever we can. Otherwise, those are my contact details, and I'm happy to have opinions on IPv6 if you buy me some Japanese whiskey.
My slides.
Give a clicker.
Oh, changes. Hey, I'm Varun Singh. I'm startup CEO. We do measurements of WebRTC in the real world, basically audio, video. We collect data. So the main thing here, I'll quickly go through my slides, which are basically a lot of results that we've seen or some of aggregated metrics. But the plea here is to ask us more questions so that we can start looking up our data for more interesting values. So when you talk about audio video in an interactive scenario, mainly you care about how quickly it gets there and if interactivity is preserved. So this is just an audio call, and typically we say that audio calls should have end-to-end latency of 200, 300 milliseconds, or 150 milliseconds, or RTTs of about 200, 300 milliseconds. What you can see here is that you have some minor blurps in the beginning, and then one big tar ranging about 3-4 seconds that is about 20, 30 seconds in the middle of the call. So a lot about internet and WebRTC today is delay and not throughput. So measuring throughput only gets us some ways, but mainly it's about to preserve interactivity in WebRTC or in audio video. So what do we measure? We measure basically per per transport metrics, per media metrics, so through the whole pipeline from the network all the way to what's being rendered. But what we ingest and spew out is basically things like annoyances, which helps our customers, which are WebRTC providers, to actually solve problems at their end. So what we do in many cases, and this is like a timeline of a call, what we sometimes do is we show disruptions so that people can go look for these events in the calls. And what we characterize as disruption is anything which has very high latency or very low throughput or very high jitter, where we believe that there would have been issues with the quality of experience. Then we correlate that with if any user feedback was received. And what we also get from our customers are like if they press pause or resume or turn off audio or video. So what we saw like some time ago was a strange user behavior where whenever a disruption would happen, the users would start to diagnose the call by themselves by either turning off video or turning off audio if they were not speaking, and and turn it on and see if things were better. So what we see is like user behavior mapping like during the call with network disruption. Another thing that we saw was that when people get really frustrated, they just reload the tab. So they press Command R. And what happened, how we observe that is as churn. So 75% of the calls we saw did not observe it, but about 25% of the calls, users were reloading the tab to see.
All right, you were the last one. So this is the end of the lightning talk session, and I was going to put up. So my proposal would be that there will be discussion, so I'm going to leave this up while we discuss for a little while. So we talked about the HOPS RG, and it's going to be renamed, but I would like to invite you guys to. So we don't have a list for this workshop, and then I don't think we need to create one, but I would invite you to join the HOPS list. We can discuss things that were brought up here more there. I don't want to auto-subscribe all of you, although I could if you guys felt that it was easier on you, so that we don't lose sort of the cohesion after this meeting ends. So this is the sort of URL where you can subscribe to the mailing list. All right. Discussion on this particular session or anything else that you still want to talk about?
This is Lin Hui from Tsinghua University, and I want to ask some questions. And I think I have already asked this question to Brian and Aaron. I have listened to all these lightning talks and keynotes, and I found something that most of you guys, the measurements are based on some kind of basic infrastructure, lower layer protocols, and something like that. And I just want to ask why there are less people focused on some more specific popular applications. I just want to ask, and I just want to gather some feedbacks from this place. Yeah, thank you.
Thanks. We're going to do the same etiquette as before. New topic, back mic, same topic, front mics. Somebody want to answer him? What did Brian and Aaron say before? So I mean, I can speculate that it's, you know, we have always sort of more focused on the network layer, but
so I'm going to be flippant and say it's because we're all old and don't understand what's popular.
Yeah, you notice that the one startup guy is actually looking at.
The answer basically came down to there are applications at the application layer that are euphemistically speaking systematically important. They're too big to fail. DNS is one of them. HTTP is one of them. We spend a lot of time looking at those. If one particular service that went and rented a lot of cloud space from somewhere and decided that they were going to run that service for a while, and that, you know, that's less interesting. We hope that the techniques that we develop in this community are useful for measuring those things as well, but it's less interesting to the entire community if we're only looking at one little tiny part of it. But if DNS goes down, we care.
Well, although, I mean, you could argue that a popular application might be Netflix, and that's a big thing, right? So
I've seen a lot of work on Netflix actually, but mainly because it is kind of when it started up, it was a little bit of a threat to the stability of the network. It's like, oh my God, this gigantic pipe just opened up. So there hasn't been much of the analysis about sort of the higher level application details, and more of the analysis is on what it looks like sort of topologically and so on and so forth.
All right. I have a question to Alberto from CADA. Yeah, great work. Very fun of you guys' work there. But I have a question about what's your definition of usage of a prefix. Because, for example, when I was measuring the churn of the particular ISP on the paper that I would use, if I would, at any point that I would measure, I would see on average 15% of the /32 is being used. And
if we had what? Sorry.
So what we did in our paper, we probed the entire autonomous systems every 10 minutes using ICMP. And in any given time, any measurement, we would see 15% of those addresses active, like lighting up, responding, out of 1 million. So, but since we measured every 10 minutes for 2 weeks' time, we saw like 75% in the end. So what is your definition of usage? Is like shows one time within your measurement period, or within your measurement period, it's used for 100% of time or X% of time?
Showed one time in the measurement period. The measurement period typically was 3 months. And the definition I said at the beginning is more general because it's an inference. And there are different types of measurements. So we say if it's an address that is officially assigned to a machine, that the machine is generating traffic on the public internet with packets with that address, of course. Right.
So you just
we used active probing datasets, and we used passive datasets. So if we were observing packets with those addresses and we believe that those packets were legitimate, so not spoofed or not destination addresses of scanning activity, for example, then we say, okay, there is an actual machine that has this address assigned and is generating traffic with this address. So it's used.
Okay, now,
does it make sense?
Yeah, no, it does. I'm just saying because, for example, what we've seen there in some radio servers, those IPs were allocated to the servers, to the radio servers that would eventually make to the users, given enough time.
Yeah.
So it's not used in that moment, but it will be in the future. That's what I'm trying to say.
3 months, I think it's a reasonable amount of time.
I would guess you. But
yeah, most of the datasets were very long, like 3 days. Yeah, there wasn't time to read the table, of course, in the slides, but they're online. Yeah.
Okay, thanks.
Thanks.
I guess it depends upon what the definition of used is, right? So if the definition of used is what portion of the address space is being used at the moment at this instant of time, then then the answer is different versus what portion of the address space is being used by ISPs. I guess that's the answer.
The idea is of
answering, right?
Performing a survey. So as I was trying to say at the end, this is an ongoing project. So we want to have longitudinal data sets, typically representative of 1 year, or let's say 6 months. That's the target. So I don't want to see what's used that day. I want to know what is in general used by providers and so on. And there is a lot of space that it seems is totally unused.
Yeah, that reminds me of your work, actually, the one you presented at AMC about when you should stop the ping, how long you should keep. So the longer I think you keep probing, the more busy we will be able to see in the end. So it's hard to create a cutoff point, but 3 months, I would guess it would be okay.
Yeah. Well, we show that in the paper too, that there is an evolution over time. I think there is a graph there.
I think the bottom line, Alberto, is that your result was not intuitive, so we're going to keep poking at it. It didn't match our intuition that half the routed space isn't used.
What is not intuitive exactly?
That half the routed space isn't used.
That routed space is not
half the routed space is not used is what you showed.
Yeah.
I'm not saying you're wrong.
Yeah.
I'm saying it didn't match our intuition. Okay. So we're going to keep poking at it.
Yeah.
Until we're reassured.
I would like to keep poking at it in the
That's
bar.
not bad. That's not bad.
Okay, something that helps, we had ground truth for at least one autonomous system, was a large network. And we verified that in that period of 3 months, no machines, like, I don't remember, it was 20% or 30% of what they were announcing on BGP was not generating a single packet. Like we had net flow records for that network. I think it was the Swiss research network, and no IP address was generated.
Right,
Not a
right.
single
I'm not-
packet with those IP addresses.
I'm not saying I think you're wrong. I'm just saying it was surprising, so we're going to keep poking
that's
to
great.
try to understand
I
the
thought you-
measurement.
Honestly, I didn't expect you to be surprised. I thought that every operator knows that they are not really using all of
We
the
need to
addresses.
move on from
Not
this
using
topic.
all is a long way from not using half.
Yeah, that's good. Okay.
Anything further on the session?
Hello, this is Zhe Lai from Tsinghua University, and I'm a newcomer to the IETF. So I have a little question about the motivation of building a new standard. So as we all know, currently we have many cloud storage services just like Dropbox and Google Drive and OneDrive. So these cloud providers may provide their APIs. So maybe many third-party applications can use these APIs to communicate with this cloud. For example, if we combine the Gmail with the Dropbox, so we can easily select a file from our Dropbox as the email attachments. So if we combine the Facebook with the Google Drive, so we can easily upload a photo from our Google Drive. So maybe I'm wondering if we can make this APIs, if we can standardize these different APIs, because I just rethink the email protocol, just like SMTP or IMAP. So
Standardization typically happens when people want to interoperate, right? And so for this particular example that you use, like the storage protocols, right? If there's an interest by different vendors to link their clouds together or their storage systems together, then you will probably see the need for a standard of some sort.
Okay.
That would be my guess, right? So obviously the IETF, we can write a standard, but it's probably one that's not going to see deployment unless some of the people who actually run the services are saying, we want this, and yes, we're going to do this. And ideally, they're going to say, yes, we're going to do this, whether or not you're going to standardize this.
Okay.
But that shows the deployment opportunities.
Yes.
All right. I see empty queues, but Alberto's coming. You can't talk about that.
I cannot. Just one thing.
Okay, go. No,
about
what it is.
No, about the surprising result of the 50%. Randy. No, but this is interesting. It gives me an opportunity. He's right. It's surprising, and it's good. You want to keep poking. The best way to keep poking is giving us data, sharing data, because this is an open question. So we want to really understand how much space is left in there, right? We know that there is a part that is not used. We know that we need to infer and to guess, but there is a space that is still unknown. So we need additional data sets. We believe that you can share data sets without sharing sensitive data. So please come talk to me if you want to poke. Thanks.
Thank you.
Yes, along those lines, any operator here would be willing to analyze their own radius logs, just tell what's the percentage of the IPs they actually use? Because that's what we did. We had a look to have a one that could do that for us. But like the big ones would be interesting.
I have to add something, sorry. When I talk about sharing data, in this case, my perspective is slightly different. I don't ask you to share information about your own addresses. That's why I believe it's not much sensitive, because I ask you to share information about addresses that you have observed in a long period of time with no content, no timestamps, except for saying, okay, it's in this year, and that's /24 granularity. So I'm not even asking to share information about how you use your own IP addresses. Like if you are a large provider, probably your users talk to the rest of the world, right? To a lot of other IP addresses, a lot of other networks.
It's probably your request better made sort of to Nanook or some form like that. But you will find operators here, like there's sitting one right there, Phil, who you talk to. So there's about 10 minutes left that I want to sort of, well, if you want to respond to him, go. I want to wrap this up soon because I think I need a beer. So the question came up, so in the beginning I said this is likely going to be a one-time thing, and I still believe this particular workshop on this particular set of topics is probably going to be a one-time thing, but I do want us to find a way to increase that, Venn diagram intersect in the middle. And if any of you have ideas of what we can do in the future, there's the HOPS mailing list, right? So for example, if we started a research group that is sort of focused around facilitating data sharing, like Miria and Brian are trying to do, that would be one thing that could turn into such an effort. If people wanted to organize sort of the inverse of this workshop at IMC or some other academic venue and try and make standards and operators come, I'm pretty sure that I at least would, and then Randy and others that are on our side here would try and maybe you're objecting to be lumped in with the ITF crowd. But we would try and help, because I think I got a lot out of this, and I'm hope that you did. But we need to keep talking, right? This is only a beginning, and I actually hope that you found the long breaks useful to be able to sort of casually chat with people, because I think the sort of collaborations that are coming out of this are probably the most visible result, hopefully.
I have feet in all three camps. I'm just saying it hurts.
Yeah, I can see that. All right, then let's all move over to the hotel bar, I guess is what we're doing. Thank you very much for coming. I think this is useful. Stick around for it. If you still want to come to the ITF week, send me email. We might still be able to finagle a day pass or something if you're still here. Thanks, guys.